the fact that it's mounted on the side, like so, and this is its initial position. It's going to swing downwards to be in this position. And correct me if I'm wrong. Did we talk? Didn't we do this yesterday? Like, didn't I have the little thing set up and we let it flop down there? Yeah. So I mean, we've seen this. I'm not saying this is easy. There's quite a bit to do here, but I'm saying that we talked about it a little bit. This is a conservation of energy problem. And if you're trying to figure out how you can tell, and look, you guys who want to figure this out, and want to be good at this, you got to look for the signs. There's signs in this problem that tell you to use conservation of energy. And the biggest sign is the center of mass changes its height. That's the biggest sign that this is a conservation of energy problem. The center of mass starts here and ends here. Once you see that, conservation of energy is the likeliest place to go. We only have 3 topics, right? If you boil it all down, it's either Newton's laws, conservation of energy, or conservation of momentum. It's going to be one of those 3. I mean, there's other side stuff like, gravity and orbits, but the big parts of our class have really focused on Newton's laws, energy, and momentum. This says energy all over it. There's no collision, so there's no reason to think about momentum. And the reason it can't be Newton's laws is even if it was, Newton's laws would be the hardest way to do this. Always start with conservation of energy if you can. But the thing that really says it is the center of mass starts at this height, ends at this height. So set the lowest level as your reference level. That's how we've done all conservation of energy problems. Determine what we feel is an appropriate reference level. And so I'm going to say that this is my reference level. And start identifying what the height is for MGH. There's no spring involved, so I'm going to use gravitational potential energy. It makes the most sense. H in this case has got to be whatever that height is, and this height is L over 2, or in the case of this problem, half a meter. It is a meter stick. We actually have numbers to go with it this time. Now, you know me, I like to put the numbers in at the end. Some of you like to put the numbers in right at the very beginning. You could. You have the mass. It's 90 grams. I'm still going to leave all the numbers for the end. Because I feel if you can do the problem with the letters, then you can do both problems. You can do problems that have some symbols in them only, and you can do problems that have numbers in them. If you always plug in the numbers in and not practicing doing the symbolic stuff, well, then you're only good at one of them. So I'm always going to do everything symbolically. When it makes to the bottom, we say that it has kinetic energy, but we're going to call it rotational kinetic energy because the object has a pivot point that is fixed in place. Now, this won't always be the case. We will have objects that don't have a fixed pivot point. But for now, we're keeping it relatively straightforward. So if it's got a fixed pivot point that's fixed in place, the only kind of energy it will have is rotational kinetic energy. If it doesn't have a fixed pivot point, then it can have both. But in this case, it has a fixed pivot point, so it only has one. And that's going to be 1/2 I omega squared. This won't tell us the answer to the problem directly. It's going to tell us the answer to the problem indirectly. Now, I'm going to keep going a little bit, but we need to identify something that is in this problem that has not yet been, kind of narrowed down, and that is, it's not about the mass, it's about the moment of inertia. Good morning, teachers. So, we have to identify what we're going to use for our moment of inertia. That's a bar rotated about its end, so that's 1/3 mL squared. Yeah, I mean, M is 80 grams or 90 grams, L is 1 meter, but again, I'm going to do it symbolically because I think that's a better way to go here. So let's kind of keep going here. It's this amount of energy equals this amount of energy. Have a nice breakfast, guys. So we'll go with mg L over 2 equals 1/2 1/3 mL squared times omega squared. All right, that's it. Find omega. Now, again, we can start canceling stuff out. Cancel one of the L's, cancel the half. A bunch of that stuff cancels out right away. And looks to me like we'll have 3G over L equals omega squared. I think that's what's left. Somebody should check my algebra, but I'm pretty sure that's right. Now, that means omega is going to be the square root of 3 times 10 over 1. All right, the length of it is a meter. So square root of 30, which is what, like 5 1/4? What's that? So 5.5. That's radians per second. Now, that's not the answer to the problem. So the answer to the problem is to figure out how fast the 80 centimeter mark is moving. Well, the 80 centimeter mark is this far away from the axis of rotation. So velocity equals omega times r, or 5.5 times 0.8. And that's how fast it's going to be moving. And I don't, that's not much. It's like, what, 4 1/4? Is it 4 point what? 4.4? There it is. That's it. The mass didn't even matter. So I'm glad I didn't worry about that. The mass will matter in the next part of the question. What do you think? Is this terrible? This is the kind of stuff. This whole set of problems is this stuff. So the next problem is to find the force. We're going to need that velocity to do so, but this is part of the problem that I think is actually harder. So I'm going to assume that you guys have that in your that number sitting right there, and I can kind of come over here and deal with the problem a little differently. This, when you're asked to find a force, you don't have many options for what to do. You're likely going to use Newton's laws. Very seldom do you get to use something else. And in this case, there are clues as to why to use Newton's laws. The first clue, it's circular motion. So because I see circular motion and I'm asked about a force, that should be a clue. So if you're looking at what I use as my deductive reasoning here, and if you're trying to take good notes, that's the clue. Right? It's traveling in a circle and you're asked about a force. That's going to be this. Now, I'm going to shrink it down a little bit because there are only 2 forces on the system. There's an upward force here on the pivot point, FP for force on the pivot. That's what we're asked to find, right? How much force is required by the pivot to hold the meter stick in place when it passes through the vertical? So I'm talking about the point where the center of mass, which is experiencing mg downwards, passes through the vertical. This is the problem. There are 2 forces, FP upwards minus mg downwards. I'm going to choose upwards to be positive on purpose because it's traveling in a circle and it equals the centripetal acceleration. So my unbalanced force has to be in the direction of the center of the circle. So that's why this one, that's where the center of the circle is. So I'm looking at the upward force. Now, you have a choice on whether to use v squared over r or you want to use omega squared times r. This part is not obvious and is new information. This whole thing is about the mass, not about its shape. So this is about where the center of mass is moving. I'm bringing it up because that's either the velocity of the center of mass or omega for the center of mass. Now, we already have one of those, but if you decide to use the velocity of the center of mass, well, you haven't found that yet. That's the velocity of the 50 centimeter mark. You'd have to find that first, but we already have omega. So I'm going to set this equal to omega squared times r, and r has to be the distance to the center of mass from the pivot point, which is half a meter. So FP minus mg equals, now bear with me, this was the square root of 3g over L squared. Again, I'm doing my problem symbolically. I want you to see why in a minute. times r, which is L over 2. So we're at top level difficulty here. It doesn't get any harder than this, but this is pretty hard. Lots of alphabet soup here. But this all is going to be pretty manageable. You square what's in there and you get, oh, I forgot to put the M here. Sorry, guys. You should expect better of your teachers. I have to apologize. It's MA. I dropped the M somehow. So it should be M omega squared R. So there's a little tiny M right there. Not sure if you saw it because I had to squeeze it in there. So that's going to be M times 3G over L times L over 2. Do you notice the L's cancel? I'm noticing the L's cancel. In fact, this whole side becomes 3/2 mg. This side is still FP minus mg. Bless you. Bless you some more. Now, I know some of you have difficulty with math like this, and we did this problem yesterday, so I'm not feeling too bad about it. This is going to be 5/2 mg. Right? 1 plus 3/2 is 5/2. If you don't like that, then just add the number 1 and 1.5. So you get 2.5. I don't care. The answer, though, probably requires that you put in that the mass is 0.09 and G is 10. And then you'll be all happy because you'll have, numbers. And this will be newtons, by the way. All right, see, problem number 1. I think that's very doable. And since we did that almost exact problem yesterday, I don't feel very bad about it at all. New information right now. And it's the only thing I'm covering today that's new, something called the parallel axis theorem. The parallel axis theorem. Now, the parallel axis theorem allows you to shift the moment of inertia to a new axis. That's what it can do. The parallel axis theorem allows you to shift the axis to find a new moment of inertia. You have to be careful. It is called the parallel axis theorem. So you can only shift it to parallel axes. So super simple. First, you have to know the center of mass. That has to be given. But then you have to add the mass of the object and the distance of the shift squared. Now, the reason I'm writing it all out is not to insult your intelligence. It's because if you look at it on your equation sheet, it's either mr squared or mx squared. And what r and x actually mean, come on, how many times when you see r do you say radius? Like every time you see r, you guys say radius? And I try to tell you that it's not. So I don't even bother anymore. I just write the whole thing out so you understand that that's what you're doing. In the problem that we have here, we're shifting the moment of inertia. It says, repeat problem number 1. This time, the pivot point of the meter stick is shifted to the 20 centimeter mark. So it was here, and we're shifting to the 20 centimeter mark. Be careful about this. To use the parallel axis theorem, you have to start from the center and shift. Everybody understand? So the center of mass formula for moment of inertia is 1/12 ml squared. You have to start from the center and shift to the new axis. So don't fall into any traps because you're just not thinking. I chose 20 centimeters on purpose because this shift from the center is actually 30 centimeters. Right? We're shifting from the center, which would be at 50, to the 30 centimeter mark. I'm sorry, to the 20 centimeter mark. I can't even talk. But this shift is 30 centimeters. See how you could be fooled? Aside from that, though, pretty easy. 1/12, 0.8. L is 1 squared plus 0.8 times 0.3 squared. That's how the parallaxis theorem works. Now, if this were mechanics, I would not put the numbers in. We would do L, and we would do some proportion, 3/5 of L or something like that. But in this class, this might be an appropriate time to go ahead and put the numbers in, because this becomes pretty much a bear if you don't. Folks, I totally screwed up the mass. It's supposed to be 0.09, not 0.8. I don't know what I was thinking. You guys see what I'm trying to say? The moment I shifted that axis in, I changed where the reference level is going to be for the change of the mass. Car builders. Well, this is almost a meter. So when I shifted to, when we were doing the problem before, we were saying the center of mass fell to here, so we use this height. But if the pivot point is here and it shifts down there, then this becomes the change in the height of the center of mass. You guys follow me? Hopefully. All right. That's all I'm going to do. I think we're almost out of time anyways, but